Welcome back. Today's explainer dives into a truly dynamic physical property of the ground right under our feet, soil consistency. We're going to explore exactly how changes in soil moisture and applied stress completely change how soil behaves. Here's our roadmap for today. We'll be defining soil consistency, looking at the three moisture levels, and understanding Atterberg's limits. Then, we'll get into the physics of soil plasticity, the factors affecting plastic limits, and finally, what this all signifies for cultivation.
All right, starting with Section 1, defining soil consistency. To really understand how soil behaves, you have to look at the invisible physical forces acting within the soil mass itself. Basically, soil consistency is defined as the manifestation of the physical forces of cohesion and adhesion acting within the soil at various moisture constants. It's a dynamic property. It dictates exactly how soil reacts to gravity, pressure, thrust, and pull. It's also what makes a soil mass adhere to foreign bodies, and it's even responsible for what you feel when you literally rub the soil between your fingers.
And it all comes down to two foundational forces. Cohesion is the attraction of substances with like characteristics. Think of one water molecule clinging tightly to another water molecule. Adhesion, on the flip side, is the attraction of unlike materials. In this case, that's a water molecule sticking directly to a soil particle.
Moving on to Section 2, the three moisture levels. As moisture content drops, soils lose their stickiness and plasticity. They eventually become friable, soft, and then, when totally dry, hard and coherent.
First up, we have wet soils. When soils are completely saturated with water, their consistency is evaluated strictly by their degree of stickiness, how much they adhere to objects, and their plasticity, which is their toughness and capacity to be molded. This state ranges all the way from non-sticky and non-plastic, straight up to very sticky and very plastic.
Next, let's talk about moist soils. This is determined at a moisture content right around midway between air-dry and field capacity. This specific state is super important because it describes the condition of soils when they're actually being tilled out in the field. The classification here ranges from loose to very friable and goes all the way up to extremely firm, where you literally cannot crush it between your thumb and forefinger.
Finally, we have dry soils. This state is all about rigidity, brittleness, and maximum resistance to pressure. In this state, if you crush the material, it just has this complete inability to cohere again when pressed together. It usually just breaks down into a powder. Dry consistency ranges from loose and soft to extremely hard, where the soil just cannot be broken in your hands at all.
So how do all these distinct states connect? Let's get into Section 3, understanding Atterberg's limits.
Atterberg's limits sequentially map out specific water content boundaries that connect these different states of soil consistency. As water content increases, we hit three specific milestones: the shrinkage limit, the plastic limit, and then the liquid limit.
This progression perfectly visualizes the journey. It bridges the gap entirely from a solid range into a semi-solid state, progressing right into a plastic state, and ultimately reaching a liquid range, all based entirely on the water content. Let's look at the very first boundary, the shrinkage limit. This is the exact water content where soil transforms from the semi-solid state to the solid state. Once you hit this, the volume of the soil remains completely constant, regardless of any further drying. As drying proceeds, a meniscus actually begins to form at the surface. This reacts against the soil grains, producing a compression effect thanks to surface tension. Once that water tension hits its absolute maximum, any further recession causes zero increase in stress and shrinkage.
Moving further up the moisture scale, we hit the plastic limit, or the lower plastic limit. This is the minimum water content at which a soil is plastic and the soil threads start to crumble. At this stage, sufficient water has formed a thin film around each individual particle, which allows those particles to slide over one another with maximum cohesion. And here's a critical point. Tilling at a moisture content above this plastic limit results in the smearing and puddling of the soil for most crops, except for rice, of course.
Finally, we hit the liquid limit, which is also known as the upper plastic limit. This is the water content where the soil ceases to be plastic entirely and becomes semi-fluid. The water film has become so thick at this point that cohesion drops off. Because of this, the soil mass will actually flow under an applied force, acting just like a viscous liquid. Now that those limits are mapped out, let's turn to Section 4, the physics of soil plasticity.
Let's explore that pliability, the capacity of the soil to be molded, and crucially to maintain that shape after deformation pressure is removed. So how does this actually work mechanically? Well, plasticity results from the plate-like nature of clay particles, combined with the binding and lubricating effect of absorbed water forming thin films. When pressure is applied, those clay particles simply slide right over each other. They're then held in that exactiform condition by the tension of those microscopic moisture films, even after the pressure is completely gone.
And here's a really fascinating takeaway. Literally any soil can exhibit this plasticity, provided it contains more than 15% clay.
Moving to Section 5, Factors Affecting Plastic Limits. The difference in moisture content between the upper and lower plastic limits is known as the plasticity index. Soils with high plasticity indices are notoriously difficult to plow. So what actually alters this range? Well, high clay content increases the plasticity number. The presence of 2-to-1 expanding montmorillonite clay also increases the index, and so does sodium saturation. Plus, the higher the hydration energy of the absorbed cation, the higher that plastic number goes. On the flip side, organic matter actually decreases the plastic number, provided the organic matter is completely hydrated first.
Bringing it all home, Section 6, Significance for Cultivation.
Why does all this invisible physics and water film tension actually matter out in the field? It all boils down to evaluating a soil's suitability for tillage. Different forms of soil consistency absolutely dictate your tillage system. If you till soils at a hard consistency, a heavy draft is required from your equipment, and large clods are formed. But if you wait for a friable consistency, only a light draft is required and the soils are easily tilled. Because plastic and sticky consistencies are just entirely unsuitable for cultivation, friable consistency stands completely alone. It is the most important optimum condition for tillage and most agricultural operations for crop cultivation. Understanding the exact manifestations of cohesion and adhesion leaves us with a real field challenge. Since moist soil is evaluated midway between air-dry and field capacity, how will you pinpoint that precise, friable optimum condition to ensure perfect cultivation and avoid the pitfalls of smearing or clotting? Think about how the moisture constants in your own fields line up with Atterberg's limits. Thanks for joining me on this explainer.